Okay, today we're going to talk about binomials times trinomials. This is going to be section 8.4, binomials times trinomials. A lot of today's lesson is going to seem like a review. One thing that I do want to go over is when we went back to last video, we explained how the FOIL method only worked when we were dealing with binomials times binomials. So we want to kind of move away from the FOIL method when we introduce the binomial times trinomials, and we want to start talking about using the area model or using the double distributive property. I'll do an example of each. I'll do one of the area model, and then I'll bring in one geometric application problem to talk about for today. So the first example, we'll call that example 1. Example 1 is going to be x plus 4. That's your binomial times your trinomial, which would be x squared plus 3x minus 6. And so what we'll do to attack this binomial times trinomial is we will set up our area model. In this case, we would create a 2 by 3. That is a binomial times a trinomial. Okay. Perfect. I'm going to put my binomial here. It's going to be x plus 4. And then my trinomial, I'm going to put that in green. That's going to be x squared plus 3x minus 6. So just like the area model with a binomial times a binomial, we take our x, we multiply it by x squared, and we are left with here x cubed. X times 3x is going to be a positive 3x squared. And x times negative 6 is going to leave us with a negative 6x. Okay, then we're going to hop down here to the 4. 4 times x squared is going to give me a positive 4x squared. 4 times 3x is going to give me a positive 12x. And 4 times negative 6 is going to give me a negative 24. So what we want to take a look at here is our x cubed term in the top left corner there. This term right here. There are no like terms, so I'm going to pull that out for my final answer. Okay. And then I'm actually going to get rid of it because I used it. Okay. Now we have positive 4x squared. And if we look at the diagonal here, we have a positive 3x squared. So when we combine our like terms here, we have the positive 4x squared plus a 3x squared. That's going to give me a positive 7x squared. Okay. And we'll get rid of those because we used those. Take a look at our next diagonals. We have a positive 12x here and a negative 6x. So when we combine our like terms here, we're actually going to be left with a 6x. And lastly, that constant term there, that negative 24, there's nothing to combine it with. So we are left with minus 24. After we've combined our like terms, that is your final solution. Give you guys a second to copy that down. Go through another one. All right. Example 2. I will run through example 2 using the double distributive property. Perhaps that is the method that works better for you. I will show you how that method works as well. And then I will go back and do one more area model. Okay, let's just say example 2. Example 2, we have y plus 1. That's your binomial times y squared plus 2y plus 4. Okay, and the double distributive property is going to have us take the first term, that y, okay, I'm going to take that y out, and we're going to multiply it by the trinomial y squared plus 2y plus 4. Okay, and then I'm going to take the plus 1, and I'm also going to distribute that to the y squared plus 2y plus 4. Okay, so I will come back to the blue here. Actually, I'll change my color. I will distribute the y to all pieces here. Y times y squared is going to give me y cubed. Y times 2y is going to give me 2y squared. Y times 4 is going to give me 4y. Then I'm going to go in and take a look at distributing the 1 to everything. 1 times y squared is positive y squared. 1 times 2y is positive 2y. That a y. And positive 1 times 4 is positive 4. And now we need to go in and take a look to see if we have any like terms here. My y cubed does not have a like term, so I'm able to go ahead and write that in my solution, y cubed, and I kind of get rid of it once I'm done using it. Taking a look through here, what we should be able to take note here is that we have a plus 2y squared. Okay, sorry, let's make that a little bit. Plus 2y squared here. And we also have plus a y squared. So 2y squared plus y squared is going to leave us with, okay, positive 3y squared. Get rid of those, use those, use those. We've got a 4y right here, and we've got a 2y here. So when I add those two together and combine them, I'm going to be left with a positive 6y. Get rid of those because I used them. And you'll see here, lastly, that that 4 is just hanging out by itself. So I'll add plus 4 at the end. And that is our solution using the double distributive property. I will give you guys a second to copy that stuff down. Okay, I'll do one more using the area model, and then I will do one geometric application problem, and we will call it a day. Okay, what I recommend you do is I recommend you write down the problem, pause the video, attempt the problem on your own, and then replay the video and try to check your work as you go along through it. So we will call this one example 3. Okay, this is going to be my binomial 2x plus 2 multiplied by 4x squared minus 3x minus 6. Again, this is the point where the problem where I'd like you to pause the video, attempt example number 3 using whatever method you'd like, and then replay the video to be able to check your answer. Okay, so again, this is going to be a 2 by 3. It's a binomial times a trinomial. So we'll draw our little area model. 1, 2. Okay, we have 2x plus 2 right here. And we have 4x squared minus 3x minus 6. 2x times 4x squared is 8x cubed. 2x times negative 3x is negative 6x squared. 2x times negative 6 is negative 12x. So that takes care of my 2x. Next we have the 2 times 4x squared, which is going to give me a positive 8x squared. 2 times negative 3x, which is going to give me a negative 6x. And 2 times negative 6, which gives me a negative 12. Again, what I will do here is I will highlight my like terms. Here we have 8x squared and negative 6x squared, so I can combine those at some point. I've got a negative 6x here, and my like term is that negative 12x, so I can combine those at some point. And then the rest of the terms do not have like terms, so I'm able to pull out this 8x cubed. Combining my 8x squared minus 6x squared, that's going to give me a positive 2x squared. I'm going to combine my negative 6x and my negative 12x, that's going to give me a negative 18x. And this negative 12 is by itself. And that would be our final answer after multiplying those together. The last problem I want to run through with you real quick is a geometric application. Okay. So this one's going to incorporate the use of algebra the area of length, or the area of rectangles, in order to find the area of a shaded region. So I'm going to get rid of everything, clear the screen here. Drop in your geometric application problem. So we are looking for the area of the shaded region. So in order to find the area of the shaded region, we're first going to have to take and find the area of the larger outside rectangle, which we're going to have to find the area of this rectangle here, the whole thing. So we have to take the area of this whole thing first. Obviously, I'll get rid of that. And in order to find the area of a rectangle, we know that we need to use length times width. The good thing is the length and the width are given to us. So the area of the large rectangle without any missing pieces is equal to 9x minus 2 times 2x plus 7. Okay, and using the FOIL method with the first, we get first terms are going to give us 18x squared. Outsides are going to give us 63x. Insides are going to give us minus 4x. And the last terms are going to give us minus 14. When I combine my like terms, I'm going to get 18x squared plus 59x minus 14. We're going to need that in a second. Okay, that was the area of the whole rectangle. Okay. But in order to find the area of the shaded region, we now have to worry about this section. So we actually have to cut this section out or subtract it from the total area of the whole thing. But we first need to find the area of this small rectangle. And in order to find the area of the smaller inside rectangle, that's going to be, again, length times width. And there we have 3x times x plus 12. And that is going to be, once we distribute the 3x to everything, 3x squared plus 36x. Okay, so now we're taking a look here, and we've got the area of the large rectangle, okay, without taking anything from it. And now we have the area of the small rectangle inside. Okay, so what we're going to have to do is we're going to have to subtract or get rid of this blue section, or green, once I mix the blue and the yellow. We're going to have to take this section away. So we're going to have to subtract this section, this area, from the area of the total rectangle. So what we're going to do to rewrite it, and that's just Creed, the dog. He's joining in. This lesson's kind of angering him. He doesn't like geometry very much. Are you done? Are you done? Okay. So we're going to take our large rectangle, which is 18x squared plus 59x minus 14. It's the area of the whole rectangle. We're going to subtract the area of the smaller piece, which is 3x squared plus 36x. Okay. Making sure we have 18x squared minus 3x squared, and that's going to give me a 15x squared. So I dealt with this and this. We have 59x minus 36x. So that's going to give me a positive 23x. Dealt with that, dealt with that, dealt with that, and we have the minus 14 left. That's our final solution. And I will highlight that for you guys. Okay, so the biggest key takeaway with the geometric application to find the area of the shaded region was to find the area of the smaller inside rectangle and subtract that from the whole rectangle. If you guys have any questions, shoot me an email, send me a message on Google Hangouts, or drop a comment in the Google Classroom. Thanks for watching, guys.